today we're focusing on free response questions on rates. The first one is a one rate problem. So guys, for this first part, what did you do to get the number of cars that pass through the intersection? Integral from 0 to 30, okay? And, and all you have to do on your paper, because they've already called it capital F of t, is write that. Now, when you put this in your calculator, and hopefully you're in radian mode, what'd you get for an answer? Here's the nearest whole number. 2474. And do you see, is it going to be cars per minute? Wait a minute. This is in F of t is in cars per minute. What's time measured in? Minutes. You should be getting cars. Yeah. You don't have to put units. And plus, even in the question, how many cars pass through? But that's what I'm saying. Like, if they're asking you how many cars, and you've been given a rate in cars per minute, you know you're going to have to integrate it to get cars. You know? Okay, so for the second part, part B, is the traffic flow increasing or decreasing at t equals 7? What are you going to do? All right, Shannon. Correct. You're just going to plug 7 right into the function. Now, when you have a calculator problem like this, you know, I didn't show it. We should have put this right into y1, right? And now we could write on our home screen of our calculator, you know, if we had it stored in y1. So as far as the work I'd have to show, I just have to say that I'm plugging the 7 into f. But what I would do in my calculator is y1 of 7. And do you get a positive or a negative? What do you get for that one? And it's positive? Yes, Ellie. Oh, it's traffic flow, not the number of cars. You know what, guys? That is actually true for this one. I looked at that too quickly. Is the traffic flow, is this increasing or decreasing? We have to find out if its derivative is positive or negative. No, that's okay. So what we're given, the function that we're given is f of t, and that is the traffic flow. All right, so if you want to know if any function's increasing or decreasing, we have to see if its derivative is positive or negative. So let's talk about how you would do this in your calculator. So let's say that you had this traffic flow function stored in y1. Math 8. So we would do the n deriv. Just get this. 82 plus 4 sine q2. So n deriv y1, comma, x, comma, 7, I think it was. 7. We want to know the value of the derivative of it at 7. And now this is the positive. Is this positive or negative? This is negative. No, you don't write any of this. What you write is capital, you write f prime of 7 equals the number you get. I should be doing this one. Next one, I promise. I'll set it up on the calculator. I'll be set. And you got some negative number? Negative 148. But that's the fact that it's less than 0. No, you're not getting that? Is anyone else getting that? I'm just taking... Oh. You go to your home screen and bars. Do you see the bars button? Okay, I'm going to start looking at this a little bit. Negative 1.872. Okay. Yeah, as far as the work you'd have to show, you don't write any of this calculator stuff on your You just want to show, you know that a function is decreasing when the derivative is negative. So you're just showing this, and then your conclusion, and if you got that its derivative at 7 is negative, that means that f of t is decreasing. The traffic flow is decreasing at 7. Yeah, that's just how you put it in the calculator to do it. These are nice. You don't have to do anything yourself. I'll take a look at that one as we talk about this next. What is the average value? Ooh, the average value of the traffic flow. That's the function we have, right? So how do you get the average value of a function that you have? Is that the f of b minus f of a over b minus a? What is that she's giving us? No, that's the average rate of change. That's what Nicole's saying. If they say the average value of the function they gave you, that's the 1 over b minus a times the definite integral from a to b of that function. So since they gave us the traffic flow function, and they're asking for the average value of that function, 10 to 15, we're going to use that one. It's on the over the interval from 10 to 15. So this is part C. 1 over b minus a times the definite integral of our function. That's the work, and then we got to make sure we put it into the calculator right, and if we have as far as putting it in the calculator, if you have f of t stored in y1, you can get the answer just by plugging it in right. Let's make sure we can get that, and we got to talk about the units. Okay, good. Now, when you find the average value of a function, it's going to have the same units as the function itself. Okay? So the function itself has what for units, f of t? Cars per minute. So that's one way. I think that's the easiest way to remember. Oops. The other way would be if you got the units for the definite integral, that would just be cars, because it's cars per minute times minutes. But then you're multiplying it by 1 over minutes, so you're going to wind up with cars per minute. Yeah. Wait, when you put it in, take a look at the next one. Oh no, y1 is just the actual function. It's when you're integrating it that you put the 0 to 30. Yeah, when you go to your home screen, and then you get out of the graph and put y equals screen, so get rid of that stuff. Okay, so that was C. And then D, oh, you're going to like this part. What is the average rate of change of the function you're given of the traffic flow? That's the slope formula. Yay! All right. So the interval is 10 to 15. We did the units in that because it's the same as the units of the function. Well, if you have the function f stored in y1, to do this on the calculator, you just, on your home screen, you got to get bars, y bars, all that. F15. Now, if you want to do this all in one step, you're going to need to put some parentheses around the numerator. Minus y1 of 10. Bless you. And then you're going to divide it by 5. Or divide it by parentheses 15 minus 10. Make sure that you're getting this whole y1 thing that I'm saying. If you're not, I just want to come over and help you with that because this comes up a lot. The bars, y bars. So this should come out to be, sometimes they, 1.518. Now, and I want to talk about the units for this. What are the units of the numerator? That's cars per minute. And the units of the denominator, remember this was change of time? What is time measured in? So you have cars per minute over minutes. So what's that if we put it all together? Cars per minute squared. Okay. So 1.518 cars per minute squared. I like the one rate problems. I think they're less common than the two rate problems. What do you think about this? Okay. Do you want to try one now that like one rate on your own? Like I'm thinking like number 2006 is a one rater. Oh, that might be a little tricky. Yeah, it's good to do a trickier. Maybe we should stick with the one rate just for like another one or two, and then we'll go to the two rate ones. Okay. So if you don't mind, just skip over to 2006. Hey, they like cars and traffic, I guess. At an intersection in Thomasville, Oregon. Cars turn left at the rate of, L for left, L of t, and that's in cars per hour from time 0 to 18. So we're 2006. And it's a calculator problem. So they give you the rate at which cars are turning left. What's that? Okay. So L of t is measured in cars per hour. And the graph of L of t, the rate at which cars per hour they're turning left, is given, that they graph. All right, so A, to the nearest whole number, find the total number of cars that turn left from time 0 to 18. And so probably the first thing you should do with this is get that rate in your calculator. Let me pause this. Okay, so in this next one, we're doing this in 2006. What's that? I know, isn't that sad? When I saw that, I was like, I'm not the best. All right, so they gave us the rate L of t that cars are turning left at some intersection, and the big thing is that it's measured in cars per hour. That's important. Okay, so we already did part A together, right, guys? Did we do that or not? Oh, okay, so if you're given the rate at which they're turning left and you want to find the total number of cars that turn left, you integrate. Yep. All right, so as far as work is concerned, you just have to integrate L of t, right? Because if you integrate cars per hour with respect to time, that'll give you cars from 0 to 18. And that's why with these, you got to make sure you have this in your calculator, the rate that they gave you. It's on a scale. You guys getting the right answer for that one? It is. I don't like it when I don't think this is really worth it. Okay. entered it in Y1, and now we just get our answer. I made the window as it was shown to me in the picture. Right? You see it on the picture, like the graph that they gave you? Okay. So math 9, bars, y bars, function, comma, x, comma, 0, comma, 18. And hopefully we'll get the same answer. Now this is to the nearest whole number, so you gotta make sure you round to the nearest whole number here. All right, so 1,658. You get that? Nice. Of course. Okay, the second part, part B, traffic engineers will consider turn restrictions when the number of cars turning, when the rate at which the cars are turning left, L of t, is greater than or equal to 150 cars per hour. So this is why you need this in your calculator. Find all values of t for which L of t is greater than or equal to 150. Now, guys, you have your calculator. How are you going to tell when L of t, the graph that you have there, is greater than or equal to 150? No idea? Let's take a look. Graph y equals 150. That was good. Whoever said that. You did. That was good. Who else? I don't know why this is not letting me switch. Okay. So yeah, what you do is you just graph y equals 150. Right? Take a look at the graph. Ooh, see, we can see it. It's over. It's from this time to this time. How are we going to get these times? Intersect. And let's store them in A and B. What? Yeah, I just wrote one. You know, if you want to know when it's greater than that graph, y equals 150, because you're not going to be able to eyeball this. You're going to have to get it from the graph. So we'll get these points of intersection. 5. You would just say it equals 150, L of t equals 150, and you just write down these answers. They know you have a calculator. Yeah. Is it come out to be that nice? Oh. Oh, no. Maybe you get some credit. Yeah. Oh, yeah, we're out of the land of integers, my friends. Life is not always going to be an integer. Oh, I just lost it. I got to do it again. Shoot. When you get your point of intersection, you leave the screen and hit store alpha A. So you have it. You leave the screen, second mode, and hit store alpha A. Enter. If you don't hit enter, that's it. It's no good. Then you go back to the graph. Second calc, option 5. First curve, second curve, yes. Enter. 16.122 roughly. And we store that by second mode, store alpha B, enter. Okay, so now we know the times for which the rate at which cars are turning left is greater than 150, right? So let's see if we can answer. That was the first thing they said, so we'd write those down. Now we have to compute the average value of L over this time interval. Average value of it. There you go. Now, oh, it's so nice that we have A and B. Like, because they're actually A and B. If we write that on our paper, A equals, B equals, then we can actually, if we've written that down first, so, yeah, we'd have to write A equals and B equals. I forgot those numbers. But then for the average value, which is 1 over B minus A times L of t, because we want the average value of L of t, not the average rate of change, the average value. So it's that one. Now, as long as I had those numbers there. This is part B. So for part A, we just integrated L of t from 0 to 18. And for part B, we had to first find out for what times L of t was greater than or equal to 150, and then we could actually do this. And this we could just pop right into our calculator. Okay, and so we just do right on our home screen, 1 over alpha b minus alpha a. Now, I want to make sure, I'm just going to add an extra set here. I think I would have been fine, but bless you. Oh, shoot. Yeah. And guys, with these packets, the answers are on the back of every page, so you'll be able to check. Yes. I would go further with values that I'm going to be using in another calculation. I don't think they would take off if you went out 3 places what you wrote down. I think that would be fine, but you could throw off your answers accuracy that if you're using those values. Yes, always 3, unless they say otherwise. Yep. No, no, this is going to make you like rates. Yeah, well, we'll have to do some of those then, I think. We'll try to focus on what you hate. Okay, guys, next question. Traffic engineers. Oh, indicate units. Did we do that? Oh my gosh. So we got our answer. Now, if you're finding the average value of L, as far as the units go, it should be the same units as L, right? So it's cars per hour. And as far as the work goes, that's what I just did on the calculator. Did you guys miss that? Do you need me to go back to the calculator? You got it? All right. All right, so you saw that on the other thing. Now, let's go to C. Traffic engineers will install a signal if there is any 2-hour time interval during which the product of the total number of cars turning left, okay, the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. Whoa. In every 2-hour time interval, 500 oncoming cars travel straight through the intersection. Does this intersection require a light? Okay. Okay, now, first of all, which time period would you pick if you're looking for, like, to see if this product of the number of cars turning left, and, well, it says the product of the total number of cars turning left and the total number of oncoming cars is greater than 200,000. So we have to figure out if there's any interval. Now, we don't know what these times are, but all I know right now is that I have to integrate from some time to 2 more greater than that time. Right? Because we're trying to see, is there any 2-hour period where the total number of cars turning left is, and we're multiplying that through what? 500 oncoming through the intersection. Oh, that's 6 times 500. So is there any 2-hour time interval where this product would be greater than 200,000? Okay, so in order for this to be true, let's divide each side by 500. What would we get if we divide each side by 500? That would mean that the total number of cars turning left in some 2-hour period would have to be greater than what? If we divide this by 500, okay, let's knock off the 2 zeros. So we have 2,000 divided by 5, so that would be 400. Okay. So we're trying to, is it possible that over any 2-hour time period that this integral, so where are you going to look on your graph to get an idea? You want that to be the greatest. You're looking at the derivative, right? You want this to be as great as possible. So around what values should we check? 14, 16 looks pretty good. Let's just see how we do with that. Because that's the, you see you have the most area under there? I know, well, they're going to throw in a weird part. But you know, when you to figure out the value of a definite integral from one time to another, it's just the area, right? Area above minus area below. We're trying to see if there's any area that's going to be greater than 400. All right, so we're looking for values over here where we get the most area. So we're just kind of roughing it here. But I think 14 to 16 is a good place to start. Maybe even 13 to 15. You could do 13.5 to 15.5. We know where that max is. Remember we had that on the calculator? Yeah, remember we found that, oh wait, we didn't find that. We could get that easily though. We could just get this max and go from that minus 1 to that plus 1. I don't know. I think we'll be alright without it. I actually don't know. It's just... Oh, I'm sorry. Okay. We're trying to see if the total number of cars turning left over a 2-hour period is ever greater than 400. Greater than, what did we say, 400? I'm sorry, 400. Because it was, the product was greater than 200,000 or something. We divided by 500. No, but we're trying to see if this area in here is ever 400. All right, that's why we're picking over there. What's that? Yeah, that's because the definite integral of LFT is just the area underneath it, right? Yeah. Yeah, we're just going to see if that works. If we get values that make it work right away, we're done. Okay? If we can show there's any 2-hour time period where this area is the greatest. So let's go ahead and on here, let's figure out what math 9 of y1 So if we try something like 13 to 15 and it doesn't work, we could try something around there. But these have to differ by 2. It's supposed to be a 2-hour time period. Oh, we got one right off the bat. Yeah. I don't know. Where is it? What? I don't know. I don't know. All right, but guys, do you see that we've already got, yes, they're going to need to put in a traffic light? Okay, let's go on with this. But because you could give this as one example, you could give this value, and that already proves that you're going to need it. All right, guys, let's. I know that the weird parts can throw you, okay? But hey, that happens. But I thought maybe I want you guys to pick. Maybe we'll go to a 2-rate problem now, a rate in, rate out problem, since we did 2 of the rate in problems, just single rate problems. All right, double rate. Why don't you look through this packet and see what you'd like to, which one you'd like to try. The one we did in class. There's another piecewise function, but I don't know. I think we should wait for that one. I do want to do the 2010 for sure. Yeah. So you're gonna be. Wait. I don't know. All right, guys. I do think I definitely want to do 2010. All right. We'll go right to the piecewise. Okay, let's go to the piecewise. I got to tell you, 2010, this did throw the kids. That's why I wanted to make sure that you could see one like this. So we are doing 2010. Okay, let's take a look. So 2010, there's no snow on Janet's driveway when the snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate modeled by, they give you a lovely function, and this is a calculator. So this is the rate at which the snow is falling, f of t. Cubic feet per hour. We don't ignore units, right? So that's the rate at which the snow is falling. Okay, since midnight. Janet starts removing snow at 6 a.m. T equals 6. The rate, G of T, G in cubic feet per hour at which Janet removes the snow from the driveway, is modeled by a lovely piecewise function. So from time 0 to 6, she's removing snow at the rate of 0 cubic feet per hour. Why? She's sleeping. Yeah. Okay. So then she gets up and she goes out, and from time 6 to 7, she's removing snow at the rate of 125 cubic feet per hour. I'm just trying to think, is that really that good? Because 2 cubic feet per minute, I guess. It depends how dense the snow is. If it's very heavy, I don't know, 2 cubic feet per minute seems a little slow, but if it was heavy, I could see that. And then she's tired, so she's only removing the snow at 108 cubic feet per minute. No. Oh. Yeah. Okay, so guys, this is a 2-rate problem. Shh. If this is a 2-rate problem, do you guys see which is the rate in and which is the rate out? Okay, I just want to make sure. That's rate in, that's rate out. All right, let's look at the first part. Yeah, it's not the same rate, but it's just using the formula, using that formula. So at least, I've never seen a rate in and rate out problem where both are piecewise. It's usually just the rate out. How many cubic feet of snow have accumulated on the driveway by 6 a.m.? So we will definitely be integrating to get the number of cubic feet of snow. And just the amount that falls, she's not removing anything, right, from 0 to 6? So because we have our calculator, we get that in our Y1. I'm not good going back and forth with the calculator. This isn't responding to the board, so I'm just going to write down, yeah. We would get our answer. We would store the f of t in Y1, and we would just do, we don't write this on our paper. We just do this. And then we'll get our answer that way. But that's a nice, easy one, I think. 42 points. If you're not getting this, let me know. Your parentheses might be off or something like that, but it is in cubic feet. What's that? Oh, let me see B. Okay, so we're okay with that one? Find the rate of change of the volume. Oh, that's just, you're right. That's just rate in minus rate out. That's the rate of change of the volume. At 8 a.m. Yeah. Yeah, now here's the thing. When you want to get rate in minus rate out at time equals 8, what are we plugging 8 into? So, yeah, f of t minus g of t. So, yeah, so it'll be f of 8. That's the rate in at 8. But now what am I going to do for g of 8? 108. Okay, so you have to look at the piecewise function. At time 8, the rate out is 108. So now on our calculator, we would be able to take, to figure this out, we would type in y1 parentheses 8 minus 108. Oh, wow, we're getting a negative value for rate in minus rate out at time 8. Well, what does it mean? Okay, so the rate out's faster than the rate in, so what about the amount of snow, the volume of snow on the driveway? Yeah, it's decreasing. I don't know if they asked us that. Let's see. Nope. We just get negative, but as far as the units go, it's the same as the units for each one. It's cubic feet per hour. They didn't ask, but might as well. Okay. Now, here's the part where I remember the kids cried. Let h of t represent the total amount of snow in cubic feet that Janet has removed from the driveway at time t hours after midnight. Express this function h as a piecewise defined function, domain times going from 0 to 9. So we have to write a piecewise function for the total amount of snow that she's removed. Like, we have the rate at which she's removing snow, right, as a piecewise function. But we want to come up with a piecewise function for the total amount at any time. So this is where it gets interesting. I'm just going to write down my g of t. That's the rate at which she's removing snow. So let's just think about this logically, all right? So h of t is the total amount of snow that she removed. Well, let's talk about the first 6 hours. Could you tell me for the first 6 hours how much snow she removed if she's removing snow at a rate of 0 cubic feet per hour? 0. So any time in there, the total amount of snow that she's removed is 0. Because she's removing snow at a rate of 0 cubic feet per hour. So how much snow has she removed for the first 6 hours? 0. Okay. But now she's actually shoveling. And she's shoveling at a rate of 125 cubic feet per hour. Now, let's think about it. What if she shoveled for the full, well, let's just say it. So at 6 a.m., she shoveled no snow, right? What about like at 6:30 or 6? Or what about at 7? How would we figure that out? How much snow? Yeah. Okay. And what do you get if you integrate 125? Okay. So you do 125x or t or whatever, right? So you would just take the amount of time that she's shoveling and multiply it by 125. If you think about if she's been shoveling at that rate for half an hour, you would multiply 125 times, well, we're doing everything in hours, so times 0.5. What you're saying is right, but we have to think about it. Well, the amount of snow that she's going to shovel is going to be 125 times the amount of time that she's been shoveling. Well, but I have to make it good for any time, because what if she doesn't, I have to make this good for any time between 6 and 7. So the time that she's actually shoveling at that rate is not the time here. Suppose t is 6.5. Okay? What are you going to multiply 125 by? 0.5. Okay? Suppose the time is 6:45. Well, the only thing is t then, let's say like at 6:30, I would be multiplying 125 by 6.5. I don't want to multiply it just by t. T minus 6. If you take the actual time and subtract 6, I know. This is the one that I don't think they'll ever do this again, but I just thought I had to see. Let's just make sure that that works. So, right, like when t equals 6.5, the amount of snow that she shoveled is 0.5 times 125 cubic feet per hour. So, yeah, because she's shoveling at a rate of, I don't remember. But now, yeah. But you're trying to get the amount of time she's shoveling at that rate. And if she only starts shoveling at 6, and you're trying to figure out how much snow, she shoveled at a particular time, you have to subtract 6. Now that we've seen that, so this is good all the way from time 6 to 7. So if we've gotten through this much time, we know she's definitely already shoveled 125 cubic feet of snow by the time you hit 7 o'clock. But now we want to figure out how much snow altogether did she shovel for some time between 7 and 9. So if you've gotten to this time, you've already shoveled a full hour's worth at 125 cubic feet per hour. So you definitely shoveled 125 cubic feet. But we have to add to that the amount of snow that she has shoveled for some time between 7 and 9. That's 108 times, how are we going to, t minus 7 will give you the amount of time she's shoveling at that rate. Yeah, I know. Well, that's what I'm saying. That's why we got to be really strong on the other parts. So when they throw you like a weird part. Oh, but do you see why you got him wrong or no? Well, maybe to get a 3. I'm trying to think what percentage. I would say so. I would say it'd be about that. I don't know for sure, but I think that sounds reasonable to me. Out of 28? Out of the 28 no calculated, that's the 5 territory. That's where you 2/3. You want to get like 2/3. Okay. All right, let's finish up this part. Okay, guys? How many cubic feet of snow are actually on the driveway at 9 a.m.? We want to know how much snow is there. Okay. If you plug in, if you want to figure out how much snow is on the driveway at 9 a.m., you're going to have to figure out the total amount that has fallen and subtract the total amount that's been shoveled away, right? So how are we going to first of all figure out the total amount of snow that has fallen by 9 a.m.? We just plug it into the rate. That'll give us the rate at which it's falling. You got to integrate it. So if you want to find out the total amount that falls from time 0 to time 9, you integrate the rate at which it falls. So, okay, this will give you the total amount that falls. We didn't do this in part A, did we? No, we did it by 6. Okay, same thing you did in part A. What's that? You want to know the total amount of, you want to know how many cubic feet of snow are on the driveway at 9 a.m. So we want to figure out the total amount of snow that falls from time 0 to 9. And then we want to subtract the total amount of snow that was shoveled away from time 0 to time 9. Yeah. Now, here's the thing. We just came up with it. Whenever you're doing a problem, realize they're going to use something from a previous part. If you want to... Yeah, you just subtract. We just came up with a piecewise function for the total amount of snow that was shoveled at any time. We want to know how much was shoveled at time. So yeah, it'll be minus h of 9, which is what you guys are telling me. I'm just going to write that out here. So this we'll have to go to the calculator for. But then the other part will just be 125 plus 108 times 9 minus 7. See ya. So this part is easy enough. So she shoveled a total of 341 cubic feet, and we just have to subtract that from the total amount that falls. And we get to 26.335. Now, I don't want you to like think, oh, this is how it's always going to be with these, but you have to see like the worst ones to see what's out there. We're doing rate problems. You have 15 minutes of question. Bye, girls. Yeah, the free response question. So, we're looking at 2013. Now, they always make these word problems something like, well, you can't even relate to it, but so they just so it'll turn you off. You have to just focus on it. So G of T is the rate at which unprocessed gravel arrives at a gravel processing plant. And I put that in Y1 because that's the rate at which it enters, at which it arrives, from 0 to 8. At the beginning of the day, it has 500 tons. They also give you a rate out because it's the rate the plant processes the gravel is 100 tons per hour. So both the rate in and rate out are in tons per hour. And you always want to put the rate in Y1, rate out in Y2, and rate in minus rate out, the rate of change in Y3. Because that's how we set up the problem. Now we're going to go, see, this is what's not working. All right, so go to here. Okay. So the first part, find G prime of 5. So that's nice, right? G prime of 5. You've got G stored in Y1. So you just pop that into your calculator, right? Doing the end deriv. And you put in your Y1, comma X, comma 5. And you get your answer. You guys said it came out to be negative. Whoa, that's hard to see. Okay, I'll tell you, I'll write what it is. It's negative 24.588. Now the units we have to give, okay, whenever you get the derivative, to get the units you divide. So G prime is dg dt. So the units of G would be tons per, I'm sorry, tons, what is it, tons per hour? Okay, that's what G of t is measured in, and you have to divide it by the units of time, because this is, I know we call it G prime, but that's dg dt, you divide. So it's tons per hour squared. So this one, did they say they said indicate hours? Using correct units. So our answer would be this number, negative 24.58 tons per hour squared. Now, they said to explain in the context, so that just means the rate at which it's arriving, it's negative at time 5, right? So the rate at which it's arriving is it increasing or decreasing? So it's decreasing by time 5. So the rate at which gravel's arriving is decreasing, and even if you didn't say by the amount, it's decreasing by 24.587 tons per hour at time t equals 5. Anytime you get the derivative of something as negative, that just means that whatever it's the derivative of is decreasing at that rate. What's that? This is for A. Wait a minute. No, A says just find G prime of 5, so we used end deriv to get it. Negative 24.588. The units are tons per hour squared. And as far as interpret that, just because we got the derivative was negative, that just means the rate at which it arrives is decreasing, because this is the derivative of that rate. Oh, I don't know. I didn't look ahead. Oh. Oh, no, but yeah, but to know if the amount increases or decreases, now we have to consider not only rate in, but also rate out. Here we only took the derivative of G, the rate in. Okay, so for part B, find the total amount of unprocessed gravel that arrives during the hours of, so all we care about is the amount that arrives. So what did you guys do for B? We integrated just G of T. Yep. Yeah, because they just want to know the total amount that arrives. So for part B, you're just going to integrate from 0 to 8 G of T. And you do this by going to your calculator and using math 9 on Y1 from 0 to 8. Now, did anyone get a number for that? What did you get? 825.5. Oh, I'm looking at the wrong one. Yep. 825.551. And the units would be tons, because when you integrate, you multiply units. So tons per hour, hours, you're going to get tons. So that tells you how many tons of gravel have arrived at this plant. Okay, now here comes the good parts are C and D. Is the amount of unprocessed gravel increasing or decreasing at time 5? You have to know if rate in minus rate out is positive or negative at time 5, right? Or you can see if rate in at time 5 is greater than or less than 100. That would be another way of looking at it. Did anyone do it one way or another? Bye, guys. Bye, guys. What did you do, Jan? So you did g of 5 minus, uh, the 500 was just how much was there to begin with. Oh, okay, so you did them like separately. So if you integrate the 100, 100t, and yes, you're absolutely right. That's very good. So different ways to do this. But to see if anything's increasing or decreasing, oh wait, you're getting totals if you're integrating. All we care about here is it increasing or decreasing at time 5? We shouldn't be integrating anything. Oh, I'm sorry. Okay. A little punch here. Alright. So, just get another. Okay, that's fine. So we want to know if G of 5, the rate in that's coming in at 5, minus the rate out at 5, which is just 100, which should just be 100. If we want to know if that's positive or negative. We just want to know if the rate is positive or negative, not like the total amount. Like, I think you're figuring out over 5 hours, the total amount out would be 500. Okay, but if you just want to know if some quantity is increasing or decreasing, you just want to know if its derivative is positive or negative. And the derivative is rate in minus rate out. But you have, but the first part, so all we have to do on our calculators is just take y1 of 5, that's telling you the rate at which the gravel's arriving at time 5, and then subtract 100 and see if we get a positive or negative value. Some people would just figure out what the rate it arrives at 5 and just see if that's greater than or less than 100. So do you know what if this came out to be positive or negative? Like that. Yeah, because, well, if you subtract 100 from it, you have 98.141 minus 100. Because if you just take G of 5, that's 98.141. So 98.141 minus the rate out. You could have just figured this out, said, oh, well, that's less than 100, so rate in is less than rate out, so it's decreasing. Or you could just say, oh, rate in minus rate out is negative, so it's decreasing at t equals 5. Hmm. Yeah. What it, did you get something was negative? Oh, you didn't account for the rate out? I would, I'm not really 100% sure because I have to see the scoring guidelines to see what they say. I'll have them for you by tomorrow and then we can see that. But yeah, anytime they want to know if anything's increasing or decreasing, if it's a rate in, rate out problem, you have to figure out rate in minus rate out. So the amount is decreasing at t equals 5 because you could say the rate in is less than the rate out, or you could say rate in minus rate out is negative. All right, and then the part D, this is the good part. We'll see if you get this. So what's the maximum amount of unprocessed gravel at the plant? This is when you have to see how much you have. So what times did you guys consider? Yeah, and you have to make sure what's going from positive to negative is rate in minus rate out. So it has to be where G of t minus 100 goes from positive to negative. It is 4.9. When you want to find out where rate in minus rate out, bye-bye, where rate in minus rate out goes from positive to negative, just graph rate in minus rate out. You put that in Y3. You turn off the other functions so you don't get confused by them. You go to their equal sign and press enter. You just graph Y3. Oh, I don't think my window's so high. But you care where it goes from positive to negative. I just have to fix my window a little bit. We'll see if it works. I don't know if I went far enough. But you get the 0, second calc, option 2. Bye, guys. Left bound, enter. Right bound, I gotta wait till the y's go negative. Okay, enter. Yes. Oh, I don't know if I can. Okay. 4.923, you're right. Okay, so that's the time, and I'm just going to store that because I'm going to need that in a second anyway. So you leave that screen, and you hit store alpha A, enter. Okay, and I can write A on my paper. 4.923 was around. Now, the amount of gravel that's actually there, I don't have a fancy name there. At time 0, they gave that to us. Did you get that part? That's 500. How are you going to figure out how much gravel you have at this time? Rate in minus rate out. So G of T minus 100 from 0 to this number here. Now, yeah, 4.923, whatever it is. Now, it's nice when you have this whole thing stored in your calculator to put this in. Because I'm just going to integrate y3 from 0 to that number and add it to 500. So 500 plus math 9, y3 bars, y bars, function, comma x, comma 0, comma alpha A. Do you guys get 635? Okay, so 635.376. Okay. And then if you've done all that to get how much gravel you have at time 8, you're going to take how much you had to begin with and add the change from 0 to 8 of G of T minus 100. Oh, you know what, guys? I didn't do something that we have to do still before we finish answering this question. We'll get this answer, but you're going to tell me one thing that I didn't write here that's really important. Yeah, as far as my justify, why am I just checking out these values? Okay, and where the derivative changes from positive to negative. Yes, you actually have to write that. Yeah, you have to say the absolute max can only occur at an endpoint, or where I would just say G of T minus 100 changes from positive to negative. Well, part D is going to be worth, like this part, I still put in the calculator, but I'll tell you right now. Just go back to it. It's annoying. Oh, right, no. I know, and it's going to get worse. Okay, let's see. Oh, this one, usually it's worth more points. This one, it was only worth 3 points. They didn't actually. It's 1 point for finding out where rated minus rate out of 0, that 4.923 number. 1 point for your final answer, and 1 point for the justification. They didn't say it in this one. I've never seen them say it before. I want you guys to always say that, because in every other one they would say this is the maximum amount. where's the justification? Well, this chart is justified, but every time you do one of these, say it could occur at an endpoint or where the derivative goes from positive to negative. I think that's really important, but it's not here. All right, so the number that we had for the last one turned out to be 525.55. If you're okay with that, you just go back to your last calculated entry and hit second enter and change that A to an 8. You get the 525. Bye. You're very welcome. All right, so yep. Okay, next problem. Because that one was done. So a lot of people started 2004. I don't have it. Let me just pull it up. I don't have it with me. I didn't